Welcome to Mathematical Finance. Have you ever wondered how professional traders and risk managers measure the hidden dangers of a stock? Today, we are going to explore volatility estimation, a fundamental mathematical concept that helps us quantify the unpredictable swings and chaotic movements in financial markets. Let us dive in. Let us start with a simple analogy. Imagine you are a passenger in a car. If the driver stays on a smooth, straight highway, your ride is calm and predictable. But if they suddenly swerve and accelerate on a bumpy dirt road, the ride becomes chaotic. In financial markets, volatility is exactly like the bumpiness of that car ride. It measures how wildly the price of an asset swings up and down over time. Estimating this bumpiness is crucial because it tells us exactly how much risk we are taking. Now that we understand the intuition, let us look at this visually. On this graph, the horizontal axis represents time in days and the vertical axis shows the stock price. The blue line represents an asset with low volatility. Notice how it follows a relatively smooth and steady path. In contrast, the red line represents an asset with high volatility. It experiences sharp, unpredictable jumps and crashes. This visual difference is exactly what we want to capture mathematically. So, how do we measure this mathematically? In mathematical finance, volatility is formally defined as the annualized standard deviation of the continuously compounded returns of an asset. Let us break that down. A return is simply your percentage profit or loss. Continuously compounded means we assume growth happens smoothly at every fraction of a second, which we calculate using logarithms. Standard deviation measures how far these returns spread out from their average. Finally, we annualize it, scaling the measurement to a full year so we can easily compare different assets. To estimate volatility, we first need to calculate the daily returns from historical stock prices. We do this using the continuously compounded return formula. Here, U sub I represents the return for a specific day. S sub I is today's closing price and S sub I minus 1 is yesterday's price. By taking the ratio of today's price to yesterday's, we get a simple growth factor. Applying the natural logarithm converts this into a continuously compounded rate. If the price goes up, this return is positive. If it drops, it is negative. Once we have calculated the daily returns for a certain number of days, we need to find their average. This formula calculates the sample mean, denoted by U bar. We simply add up every individual daily return from the first day to the last and divide by n, which is the total number of observations. This average represents the general drift or baseline trend of the stock price over the measured period. Volatility will measure how much the stock deviates from this very baseline. Now we calculate the sample standard deviation, denoted by S. This tells us how much the individual daily returns wander away from our average return. We subtract the average from each daily return and square the result so that positive and negative swings do not cancel each other out. We then sum these squared differences and divide by n minus 1. We use n minus 1 instead of n to correct for statistical bias since we are looking at a sample, not the entire history. Finally, taking the square root brings the measurement back to the original units. The last step is to convert our daily standard deviation into an annualized volatility, denoted by the Greek letter sigma. In finance, variance scales linearly with time, which means standard deviation scales with the square root of time. So we multiply our daily standard deviation S by the square root of n, where n is the number of trading periods in a year. For daily data, n is typically 252, accounting for weekends and holidays. This final sigma is the standard measure of risk used in financial models. Before we move on, let us see this with a concrete example. Suppose we observe a stock's closing prices over 5 consecutive days: 100, 102, 101, 104, and 103. First, we calculate the 4 daily continuously compounded returns. For day 1, we take the natural log of 102 divided by 100, giving 0.0198. We repeat this for the remaining days. Notice that when the price drops, like on day 2, the return is negative. Continuing with our example, we now have 4 daily return observations. So, n equals 4. Our next step is to find the average of these returns. We add all 4 daily returns together and divide by 4. This gives us an average daily return of 0.0074 or 0.74%. This means that on average, the stock grew by a fraction of a percent each day. This average sets the baseline for our bumpiness calculation. Next, we calculate how much each day deviated from that average. We subtract the average return from each daily return, square the differences, and add them all up. This gives a total squared variance of 0.00122. To find the sample standard deviation, we divide the sum by n-1, which is 3, and take the square root. This results in a daily standard deviation of 0.0202. This means on a typical day, the return fluctuates by about 2%. Finally, we must annualize this daily figure to make it useful for standard financial models. Assuming there are 252 trading days in a standard financial year, we multiply our daily standard deviation by the square root of 252. This gives us a final annualized volatility of 0.3207 or 32.07%. In practical terms, this tells a trader that the stock's price is expected to fluctuate within a range of roughly 32% over the course of a year. Now that we have used daily data, let us look at another example using weekly data. Suppose an analyst observes weekly closing prices of 500, 490 and 510. The process is identical, but the time scaling will change. First, we calculate the 2 weekly returns using the natural logarithm, giving us negative 0.0202 for the first week and positive 0.0400 for the second. Adding these and dividing by 2 gives an average weekly return of 0.0099. Continuing with our weekly data, we now calculate the standard deviation. We subtract our average from each weekly return, square the differences, and sum them up. Since we have 2 observations, n-1 is simply 1. We divide our sum by 1 and take the square root of the entire expression. This gives us a weekly standard deviation of 0.0426. This means the fund's weekly returns deviate from the average by about 4.26%. To finish this calculation, we must annualize our weekly standard deviation. Since there are 52 weeks in a year, our time scaling multiplier changes. We multiply our weekly standard deviation by the square root of 52. This yields a final annualized volatility of 0.3072 or 30.72%. This shows that whether you use daily or weekly data, the mathematical mechanics remain exactly the same. You only adjust the final multiplier to match your data frequency. So, we have proven that we can calculate volatility from historical data. This brings us to an important question. Why does this matter? Estimating volatility is arguably the most important task in modern financial risk management. Without it, mathematical models like the Black-Scholes formula completely break down. Banks use these estimates to calculate value at risk, determining potential losses on a bad day. Traders use it to see if options are overpriced. In everyday terms, volatility estimation is the financial equivalent of a weather forecast. It tells you how severe the storm might be. Let us summarize what we have learned today. Volatility is the mathematical measure of the historical bumpiness of an asset's price changes. We calculate it by finding the standard deviation of past continuously compounded returns, and then we scale it up to an annual figure using the square root of time. This single number quantifies financial risk and serves as the critical heartbeat of option pricing models. You now have the foundational tools to measure and understand unpredictable market swings. Great job following along.